Previously we talked about symmetric encryption. In this movie I'd like to talk about asymmetric encryption. Again, this is excerpts from chapter 8 in your book. I've added some material. The primary weakness of symmetric encryption is keeping that single key secure. Remember, symmetric encryption is fast, however, but you have this weakness, which is also known as key management, or that's what they call the issue. Key management poses a number of significant challenges. To solve this problem, we have, or some very smart people have developed something called asymmetric encryption. This is also called public key cryptography. This uses two keys instead of one. The private key typically is used to encrypt the message. The public key typically is used to decrypt the message, although there's some variations on this. They're both very, very large numbers, and they're created at the same time in a mathematical operation that it's not hard to create the keys. But the idea is that even if you have one key in your possession, for example, even if you have someone's public key, mathematically there's no way to determine what their corresponding private key would be, short of simply doing a brute force attack. By brute force I mean you try every possible option until you discovered it. And since these are very, very large numbers, there are a very large number of possibilities that you'd have to check. So that's the concept behind this. So what you have is you have two very large numbers that are selected at the same time by the selection algorithm, and one of the numbers, and it doesn't matter which one, you basically declare it's going to be the private key, and you keep it secret or private, and the other key you make freely available in the public domain. And we'll see how this works in the next 3 or 4 slides here. Here's the book's picture on this, and again what you want to realize here is the general flow of this has been folded back on itself, so it goes this way. So again, we have a sender and we have a recipient, and we have plain text we want to send. We feed the plain text into the encryption algorithm, or the cipher, and we use the private key of the sender. Okay, this is important. So now we have the ciphertext here. We can transmit this across the public network. We have the same ciphertext at the recipient. We feed the ciphertext back into the cipher. This time we use the public key of the sender. And remember, we're at the receiving end here, and since we're using the public key of the sender, that public key is going to be readily available to us. In some situations, it's actually sent with the message. So it's not hard to get the public key. So the output of the cipher is equivalent to the original plain text. Now, if you compare this to the graphic that's in the book for the symmetric encryption, everything here is the same, except asymmetric encryption uses different keys. Another thing, there's a couple more things that are different. The keys are much longer. And by longer, I mean 1024 or 2048, 4096 bits, long in those ranges. You pick one. And the longer, the more secure. The second thing is this whole the whole process here, since we're dealing with longer keys, the process is slower. So this is the way you'd send an encrypted message. And actually, this is not the way you'd send an encrypted message. This is the way you'd send a message that is verifiable, that it come from a certain person. This is more or less equivalent to digital signing. And we'll look at some other options here in a moment. So with this one, note here the process, note that we have different keys. We'll talk more about which one you grab to do particular things. So it's an okay picture, but it's not really showing you, all the possibilities. And I'm going to do that on the next slide. So I'm going to show you some possibilities here, and we'll just have a couple of general categories here. We'll have you and me. Now, if you want to send me a private message, I'll tell you what, let's don't go the you and me route just yet. So just forget this. Let me just erase this. We'll do the you and me thing on the next page. I'm getting a little ahead of myself here. What I want to show you here is I just want to reiterate, make sure you understand. What we're really talking about here. For example, if I have some plain text here and I feed it into the algorithm, and we'll talk a little bit later about the various algorithms that are available here, and if I use a public key here, so we've got plain text in, public key in. This is going to be ciphertext. And on the receiving end, we're going to run the same algorithm. In this case, what we're going to have to use here is the corresponding private key. We can't use just any private key. We have to use the private key that corresponds to this public key. And what we're going to get out here is, again, the plain text. Now, if we do this with another option here, we can use another way this works. Again, here's our algorithm. Feed the plain text in. If we use a private key, algorithm, the only thing that will decrypt this is the corresponding public key. And what we're going to get out here is, again, the plain text. And what I'm trying to show you here is, if you encrypt something with a private key, the only thing that can decrypt it is the corresponding public key. If you encrypt something with a private key, the only thing that can decrypt it is the corresponding public key. So this is the beauty of the system. Now notice here that you can't encrypt something with a private key and decrypt it with the same private key. It doesn't work that way. It has to be the other part of the key pair. So if you encrypt with one, you've got to have the other one to decrypt. And this is the kind of the beauty of the system. And I'll show you some things we use this for. Just as a little reminder here, the problem that we're trying to solve is how to manage the keys. And with this asymmetric encryption, one of the keys can not only can be made public, it must be made public. And the other key, the private key, is kept private. So we've already basically solved our the problem we had with the key management. Now you'll see one of the I'm going to do another video on the secure sockets layer, and that will use both asymmetric encryption and symmetric encryption. It will use the strengths of each. The strengths of asymmetric encryption is it solves the key management problem. Its drawbacks is it's slow. So the strength of symmetric encryption is it's fast. Its weakness is how do you get the secret key from one side of the conversation to the other? Well, the answer is you use the asymmetric encryption to transmit the key securely, and then you use asymmetric encryption to transmit a symmetric encryption key, which oftentimes we call session key, to the other party in the conversation, and then you use that session key to encrypt the actual conversation itself. So we'll look at that later. I'm just trying to get some of these concepts out there so you can be thinking about them. So let me show you an example. If I wanted to send an encrypted message to you, and this is one of those situations where I do want to start out with a me on this side and a you on this side. Now, let's think about what is out there in the public domain. There's my public key, and there's your public key that's out there where anybody can see them. So if I want to send an encrypted message to you, what I'm going to do is I'm going to grab or download, however you're going to put it, your public key. Okay? And this is what I'm going to use to actually encrypt my plain text. So here's my plain text. Here's my algorithm, or cipher, whatever you want to call it. And in this case, notice I'm going to use your public key as an input here. So here I've got my ciphertext, my encrypted text. Now, if you send this across the public network, this is public network. Anybody can see this. Now, think about this. If I encrypt this with your public key, the only key that can decrypt it is the corresponding private key, which only you should possess. So at this point, you take your private key, feed it into the algorithm along with the ciphertext, and what comes out is the plain text. Now, you really need to understand this. So this is what if I'm going to send an encrypted message to you, I grab your public key, which is out there in the public domain. I use it to encrypt my plain text, and I send it across the public network. For example, in chapter 6, I think it is, there's a we talk about email security. We talk about PGP, excuse me, or S-MIME. This is the concept that they use. So this is one example of how we would use asymmetric encryption, and you need to understand this. And let me show you another example of this on the next slide. Here I want to show you how you digitally sign a message. Now this is the simple version, and the graphic that's in the book, the way I explained it, is really digital signing. If you look back at that, if you just reverse the keys instead of using the sender's public key and then the sender's private key and then the sender's public key, if you just reverse those and use the recipient's public key and the recipient's private key, you would have what I just explained on the previous slide. This is how to send an encrypted message. So on this one, let's look at digitally signing, which is another very important application of asymmetric encryption. Again, we're going to have me and you, and again, let's look at what's out there. My public key is out there available, and your public key is also out there, freely available. So in this case, I want to digitally sign a message. So what I'm going to do is, what really happens here, you take a hash of the message, and I'm going to do another movie on digital signing, so you'll see this again. Hash the message, pass the hash into the algorithm. Remember my video or my movie on hashing. Hashing produces a unique, well, for all intents and purposes, a unique output for any input. So in one way of looking at it, it's kind of a fingerprint. And when we talked about hashing previously in digital fingerprints or message signing, I pointed out that we need some mechanism whereby someone intercepting the message, the man in the middle is the example the book gave, the man in the middle can't change the hash so that we can't verify whether or not the message has been changed or not. So this is how we're going to do it. We're going to take the hash of the message, and we're going to use my private key to encrypt this. So here we've got ciphertext. And on the other end, what you're going to do to verify the signature is you're going to grab my public key. So you grab my public key and use that to decrypt the ciphertext. And what you should get out, or what you will get out, is a hash of the message. Now you can take the message, which is now this. Remember, the message is actually separate from the digital signature. You can take the message, which may or may not be encrypted, like we did on the previous slide. So you can take the message, you can run it through the same hashing algorithm, be it MD5 or SHA-1. You can run the message through the same encryption the same hashing algorithm, generate a hash value, and compare it to the hash of the message that you just decrypted here. And if they match, you know that the message has not been tampered with in transit. If they don't match, something has gone wrong. There was either an error in transmission, or there's been some sort of possible man-in-the-middle attack, etc. So this is how you do use asymmetric encryption to digitally sign a message. And again, we're going to go over this in a little more detail in another movie. Let's, if you're interested in taking the Security Plus exam, there's a few algorithms you need to know about. One of the more popular ones was developed by three gentlemen called Rivest, not sure how you pronounce that, Shamir and Adelman. It's abbreviated RSA. It was first published in 1987. It was patented in 1983, and I think the patent expired in 1999 or something like that. It's the most commonly used asymmetric encryption and authentication algorithm. It's included as part of web browsers from Microsoft, Netscape, as well as other commercial products. This is what's used in SSL, the Secure Sockets Layer / Transport Layer Security, which there'll be another video on this. Key size 1024 or 2048, but you can also go up to 4096. Again, longer key sizes are slower, but much more secure. With longer key sizes, you are dramatically increasing the number of possible combinations that has to be checked by someone who's trying to crack or discover the private key for a corresponding public key. So longer keys are definitely more secure, but slower. Diffie-Hellman. The Diffie-Hellman algorithm, and this is named after two other people, does not encrypt and decrypt text. It allows two users to share a secret key securely over a public network. And once the key has been shared, both parties can use it to encrypt and decrypt messages using symmetric cryptography. Again, this is using the strengths of each of the types of cryptography. And while I'm thinking about it, I think I mentioned this before. With any method of encryption, you want to minimize the amount of ciphertext that's been encrypted with any one key. So what we do is we use asymmetric encryption mostly. This is the best way of doing it. You want to mostly use it for short messages or to send a symmetric key from one party to the other, and then use the symmetric key to encrypt larger messages or data transfers. And there are even instances where, in the interest of security, your applications will, for example, maybe every minute or so, in a data transfer, on the fly as part of the session, generate a new session key and send it across using public key or asymmetric cryptography. Again, the object is to minimize the amount of anything encrypted with any key. So you want to minimize what you actually encrypt with your public or private key, because the more ciphertext that's out there, the more the cryptanalysts have to work with, and you want to minimize what they have to work with. And by changing the symmetric key on the fly, or changing it per session, you're minimizing the amount of information that's been encrypted with that key. And also, that session key is not going to be used again. It's these session keys for symmetric cryptography they're generated in a pseudo-random way, and they're used for a period of time or maybe one session, and then next time you get a new key. So the whole idea is here you want to use symmetric and asymmetric in ways that maximize their strengths, and at the same time you want to minimize the amount of information that you're encrypting with any single key. I think we have one more slide here. Elliptic curve cryptography was first proposed in the 80s. Instead of using prime numbers as the other RSA and Diffie-Hellman does, it uses elliptic curves. This is another just mathematical way of doing it. You might have some general question about this on the Security Plus exam, but this is pretty much the amount of detail I'm going to go into it. I'm going to do another video on digital signatures. I'm going to have one on SSL. So we're not through with cryptography by any means.